I'd like to introduce, my name is Joe Corzilius. I'm just going to introduce Peter Taylor, CP Tech Center in the National Concrete Pavement Technology with Iowa State University, right?
That's it.
Make sure I get the correct one.
Yeah.
Is definitely a recognized expert in concrete and concrete pavement technology. Is going to kind of present an initial study that's being done for the NRA, National Road Research Administration, on joint associated stresses in concrete pavements. So Peter, go ahead.
Thanks very much, Joe. I appreciate the opportunity to talk about this topic again. It's actually inspired by Dr. Bernard Kai. His vision is that we keep informing people on where we are with the latest and greatest information on how to deal with joint distress. And in the long term, I think we're hoping to produce an updated version of a tech brief with some guidance on how to deal with it and to assist agencies as they come across this problem. So the process that we're working through is that I'm working with Joe, that I put together this webinar. At the end of the webinar, Lauren will be sending out a survey that Joe and I have prepared together. And in that way, we're hoping to be able to get some information back from you as practitioners on, did we miss anything? Is there anything new and interesting that we were not aware of, so that we, any guidance or references that we produce are up to date. So I'm going to spend the next 3/4 of an hour to an hour throwing out some thoughts about where we are with the mechanisms behind joint deterioration. If you have any questions or comments, feel free to type them in the chat box, and we'll try and pick those up at the end of the session. So the overview of what we're going to cover today is the mechanisms behind why we're seeing the distress that is occurring out there. The actions that we can take at the time of construction to reduce the risk, what you can do as an owner to keep an eye on the condition of your joints, and the actions that you can take once you start seeing distress occur. What can you do about it so that you can stay ahead of the damage and don't have to replace the whole system? And then we'll go through the survey questions very quickly, just so that you're aware of what's going to be coming at you. So what are we talking about? Joint deterioration. These two photographs are very typical. It doesn't happen everywhere, but what we have seen is that, particularly in small towns where the whole town looks like this, city engineers tend to get a little bit grumpy. So we're getting the center of the pavement, the center of the slab is beautiful, it's in pristine condition, but the joints themselves are starting to show signs of distress. And again, depending on how you repair them on the fly, they can start to look pretty ugly pretty quickly. We tend to see it happening more in local streets, but occasionally we do see it happening in interstates and expressways, but this is more unusual. How bad does it get? Well, it basically depends how long do you leave it. It typically often starts out as the shadowing here, so a discoloration a few inches away from the saw cut, but if you leave it long enough, you can end up in fairly severe distress. And I'm pretty sure that speed limits in this section of the city are severely lowered. Yeah, maybe it's an effective way of doing traffic calming, but I'm not sure that most engineers would agree with that. It doesn't always look the same. Sometimes it's in the form of raveling. Photograph on the right here, what we've seen is that a crack is formed about 1 inch off the original saw cut, and the material's been lost, and it's been repaired. 1 inch away, it's happened again. And in this case, it's happening a third time. You can see a crack starting to form, a third layer of distress. So it's stepping its way out from the original sawn surface. It keeps on going even after you repair it. And that may play into the conversation about how do we repair it? And we'll address that later on. One of the more challenging scenarios has been this one, where this is all obviously the same concrete, slip formed all at the same time, and one corner is in real trouble, two corners are showing a little distress, and the fourth corner is sitting there high and dry, proud, happy, no distress whatsoever. And that was always a challenge for us to begin to understand how that sort of thing could happen. So in summary, the things that we most often see, it's more prevalent in local streets than in mainline slip-form paving. It's not everywhere, but wherever it does happen, it does seem to be pretty significant. And there are frequent examples of it happens here and then not a little further down the road, even the next panel. Now, the photograph is of a city street in the Midwest. It's about a 2-mile length from where I took this photograph to the end of the road that you can see. The first mile was placed in June. They closed the whole road down and replaced it all. Then when that section was complete, they reopened that to traffic, closed the second mile down, and repeated the exercise. Same contractor, same crew, same materials, same source of concrete, same traffic, same environment. The section we're standing on is not pretty. The second mile is pristine. Very confusing. Now, the only real difference between these two sections is they were placed about a month apart in time. We spent a lot of time looking at this. We had a pool fund running. We had some of the biggest and brightest brains working with us, including Larry Sutter and Jason Weiss. Larry and I spent a lot of time traveling all over places where we were trying to pick up clues. We were trying to find locations where it happened and didn't happen so that we could pull cause from them and see if we can observe the differences between them. The things that we started to learn, it didn't happen in warm states. I did have one person in Mississippi telling us they thought it was happening, but they never actually provided us with any samples. So I'm not sure about that one. Generally, it's all happening in the northern states. It almost always happens where there's an abundance of water. So again, particularly in the Midwest, you know, the region 1 in this image seems to be far more prevalent. And as much as the Harris states are to the west, they do not seem to have the issue to any great degree. And again, as I've already said, it's not always the same. It seems to appear in different guises. One of the loudest clues, wherever we went, was this issue of water. And I've used this image in the past, but it's still a great one. This is a car wash for a car rental facility. So when you return your vehicle at the airport, the first thing they do is run it through a car wash. And in this facility, it's a big one at a major airport. Cars on a busy day are running out of here every 4 to 5 minutes. This section of roadway, you can see the cars come out of the car wash and turn left and go around to the other side of the building. This piece of concrete slab is just in the wheel path. The corner that is trafficked and always wet because it's continually got drippy cars driving over it. This is in a Midwest city, so it's cold, it's miserable, it snows, it gets icy. But cold, wet cars coming out here cause damage. The same piece of concrete that is allowed to dry out is not distressed. And that started to be a clue. Water is a fairly big part of this whole issue. Here's another one. These two cores were taken at opposite ends of the same slab. The one on the left, you can see, is fairly badly deteriorated underneath the joint, underneath the seal in the kerf. On the other end, it looked perfect. And that's why I pulled these two cores. One end was looking great, the other end was not looking so bad. Again, the same concrete, probably the same truckload of material. turned out that what we think happened is on the right-hand side, the crack formed or activated pretty early on and became pretty wide. And what actually happened, you can see it here, the backer rod and the black sealant slipped down to the bottom of the joint, and we filled up the rest of the joint with crud. And in effect, this whole section was fairly well protected from being wet. Here, it didn't crack out quite so early. It has cracked, but the crack width is pretty narrow. And underneath this section, it was clay. So once the water penetrated through the crack, it had nowhere to go because it was saturated. We were at the water table. So the water got trapped in the kerf. And then we got freezing and thawing cycles. We got chemical attack happening inside the kerf here. And you can see the little fingers of damage. It looks like thin flakes, almost like fingernails, layers and layers and layers of them. And that soon became a fairly typical observation. The other clues were, typically, whenever we saw distress, it was associated with abundant use of de-icing salts. The photograph on the left, you can see it still looks wet. This was about 4 days after the last snow event. But the de-icing salts are such that they don't let the system dry out. They hold the water in, and it stays wet. In this case, on the photo on the right, this is right outside my office. And again, you can see the center of the slab is really pretty and dry, but around the joints, it's still wet several days after the last snow event. So again, the de-icing salts are holding the water in place, increasing saturation. The other issue, and this is one I do want to highlight, look, as we move forward, is that typically we were seeing that it happens in pavements that are about 10 years old. And indeed, some older pavements that were really happy all of a sudden started to deteriorate relatively recently. And again, this started to be part of the clues that we used to solve this puzzle. I'm going to come back to this idea of systems that have been in place for a while, in that I'm still getting questions. People say to me, you did this work years ago, you gave us all these recommendations, and damage is still happening. Why? And often as not, when we do investigate it, it turns out the pavements that are starting to show distress now were built before people started implementing the recommendations that we were making several years ago. So I guess the point that I really want to make is that there's still a fairly healthy or fairly significant amount of concrete pavement out there that may still show signs of distress because it was built before we were able to make rigorous recommendations on how to prevent it. So we can expect this problem to keep showing up for a few more years. And that sort of plays into the discussion we're going to have at the end on how do we fix it when it happens. The other really loud clue came from a case in Iowa where paving started out in fall. And on October 15, the state specifications said no more fly ash. They kept on paving. They had a really warm season, so they kept on going for a couple of months. Eventually, they shut down. They returned back in the spring and continued with fly ash. So we had 3 completely different sections, same contractor, same material, same contract, except the middle section was placed with no fly ash. And it's a clear night and day light switch of where the fly ash is present in the mixture, there is no distress. Where there is no fly ash, the distress is pretty significant. Again, it came on and it came off as they changed the system, adapting to the seasons. And it's a fairly loud signal. You know, I've often had this discussion with consultants of saying, well, they're very worried about putting fly ash in cold weather. And I'm saying I'm more worried about not having fly ash. And that leads to a whole nother discussion, which we'll get to in another forum in a couple of months on, but wait, we're struggling to find fly ash. Yes, I know. And I'm not sure I have any short answers to that, but we're working on that. Come back in a couple of months And we'll see what solutions we've come up with. All right, as I already indicated, typically when we pull out cores, we see this thin, flaky system. That and the shadowing are the fairly loudest symptoms that we see. We also see fairly frequency this phenomenon. I call it tunneling. This is from an expressway in Iowa, and it's gone down the full length of the expressway. Look at the surface. It actually looks fine. But underneath, in the kerf at the bottom of the saw cut, it's been reamed out. I think Bernard had a different title, but this is a photo of Bernard's that I took from one of his presentations. Very similar. In this case, it's been bottom up, but it's also removed all of the saw cut and the kerf. And so, you know, it's fundamentally the same phenomenon. Lots and lots of water. In our case, in the Iowa case, we think what happened here is that the transverse joints were early entry saws, about 1 inch deep. The longitudinal saw cuts were T/3. So any material or water that got into the transverse joints drained into the longitudinal joint and then got trapped. The crew doing this repair work were telling me that any water that got into the system while they were sawing didn't drain away. These were tight joints. They had tie bars across them. Water couldn't get out, so it was trapped inside here and causing or accelerating the distress. The other cool image that gave us a fairly loud clue, this was a core also taken at Minroad when I visited way too many years ago to remember precisely when. But it was very intriguing that, look at the aggregate in this core. It's perfectly clean. It's been polished. That's phenomenally difficult to do. And it was a very loud signal. This is not an aggregate problem. It's a paste problem. The paste is being attacked, and the aggregate is remaining behind quite happily. And I've seen this in many locations around the Midwest where, you know, if you have enough raveling, what we're seeing is that there's loose pebbles lying around in the troughs where the damage has been happening. Let's cycle back to this one with the pretty corner and the other 3 corners looking troubled. It was the saw cutting industry that talked me into this probable cause, is that if you're working with a machine that isn't properly set up, or if the blades are starting to get dull, and you find that the operator is continually fighting to keep the saw running straight, it is likely that the blade on its way up and out of the cut is causing some sort of bruising or micro cracking on the back face. So one face where the blade is not actually impacting it, it's clean and it's dry and there's far less impact. It would be the left-hand side. On the back face where the blade is fighting the concrete on its way out, you're leaving behind the bruising, and that bruising or micro cracking is a place where water can collect, nasty chemicals can stay, and that's where the damage is happening. And that made a lot of sense when this was explained to me. All right, so now we come down to the real meat and potatoes of why this sort of distress is happening. One of the significant ones is this idea of saturated freezing and thawing. Here we have an image of 3 different pipettes. One is straight, one has a slight bubble in it, one has a large bubble in it. These illustrate really nicely why we need to put air voids into our concrete. If you were to cap the one on the left and freeze it, the water would expand 9%, you would break your pipette. The one in the middle, where we've got a little bit of an air bubble, you can see that it actually hasn't risen quite as high under capillary action. So there's a little bit of space. That one we freeze, the water may well have enough space to go into. Damage may eventually happen, maybe a little slower. Saturation is lower, damage will be less. In this case, on the right-hand side bubble, now the shape of the bubble has dissuaded the capillary action from continuing to suck it up. We've now got a stable, happy, empty air bubble. Saturation is very low, and so there would be no distress in this case. So, saturated freeze-thaw is when you have a system that's completely full of water, including the air bubbles. when it freezes, the water expands, the water's got nowhere to go except to jack the system open. What saturation do you need? Jason Weiss has indicated anything above about 85% saturation. Again, let me emphasize, including the air bubbles, you will start to show signs of distress. And the air bubbles significantly slow how fast that system gets saturated. And that's why they protect us from freeze-thaw distress. So we need a good air void system in our concrete to protect it. The issue about water-cement ratio is that the lower the water-cement ratio, the fewer capillary pores we're going to have in the system, the fewer amount of access of water to get into the system. And again, Minnesota has led the way for the last 15 years of imposing fairly low water-cement ratio. And the data is clearly indicating that that has been well worthwhile, that keeping the water out of the concrete, both in terms of design and detailing and in terms of an impermeable system, has been very beneficial. All right, so freezing and thawing, that's one cause. The other one is chemical. I'm going to work backwards through this slide. We quite often see this idea of ettringite forming in the air bubbles. This is fairly common. I believe I stole this image from Gerard Mulzoff. And he's managed to stain the ettringite that's inside the air voids. And the thought is that these air voids are compromised. And that may be so. I'll qualify this a little bit. What these air bubbles do actually do is that because they're now filled with a fibrous material, their protection against capillary suction is compromised. And so these things, an empty air bubble is difficult to fill with water. An air bubble fill of ettringite is extremely easy to fill with water. And so your saturation rates will go through the roof. And there are data out there, I've got data from a German paper, showing that a system like this, the rate of saturation is far higher. So your rate of distress will also be far higher. The other salt, Friedel salt, calcium chloroaluminate, can deposit out in the voids. But the big and nasty one that causes the bulk of the distress is this beast we call calcium oxychloride. This is an interesting compound, mainly because it's not stable at very low temperatures and very high temperatures. It forms and expands at around about 30, 40, 50 degrees Fahrenheit. So this is not a cold weather issue. In fact, the biggest issue comes in spring. As the weather starts to warm up and we start to shed our coats and plants start to grow and bunnies appear in the garden and life is wonderful, our concrete is suffering because it's at that temperature range that the calcium from the cement, chlorides left over from de-icing salts that haven't escaped out of the system, and water combine in a fairly complex series of chemical reactions, which I'm not going to get into because I'm a civil engineer. But suffice to say, we get 300% expansion, which is why we get these muffin top cores. These were samples tested by Larry Sutter. A lot of us were fooling around with this phenomenon 15, 20 years ago, doing freeze-thaw testing and getting confused because calcium chloride doesn't freeze until about minus 60 degrees Fahrenheit. Larry was the smart guy who put them in containers at 40 degrees Fahrenheit. And this is when the trouble really happens. At 40 degrees, all hell breaks loose. We get a lot of damage. The intriguing thing is that this compound is unstable at room temperature. So you pull a core out, you cut it open, and you give it to a petrographer and say, can you see calcium oxychloride? The answer is going to be no, because the compound decomposes and disappears during the processing. All that you can see left behind is the damage. And again, those flakes are very typical of oxychloride formation related damage. The only way we know that it's been oxychloride as opposed to freeze-thaw is the location. At the bottom of a kerf of a saw cut, the temperature cycles are probably likely to be fairly damped because of the insulation of the concrete above it. But wetting and drying, freezing and thawing, the other environmental cycles will encourage the oxychloride to drive off those little flakes. The photograph on the right comes from my lab, where one of my students took a hockey puck of concrete, threw it in calcium chloride at 40 degrees for about 2 months. And then when we took it out, we noticed that there was a bit of a step between the paste and the aggregate. And again, this makes sense because calcium oxychloride causes the paste to expand, but the aggregate does not expand. When we put this under an electron microscope, we could clearly see very clear cracking in the interfacial zone around the aggregate particles. And in fact, if you leave it long enough, the aggregate particles come loose, which ties back to that old photograph of the mineral core with the beautiful, clean aggregate particles. It's because the paste is expanded, particularly around the aggregate particles, and has been separated from them. So again, this is a very satisfactory description, and it seems to answer all of those differing clues that confused us early on. Why is this happening now? Why didn't it happen 10, 20 years ago? Well, 10 years ago it was happening. That's how we got started in researching this whole issue. 20 years ago, not so much. I think one of the biggest changes in our lives is that we've moved from ordinary sodium chloride to other exotic de-icing salts. Why? Because we're demanding safety. I'm more than happy for my children to be able to stay on the road when the weather is cold. So the mag chlorides and the calcium chlorides that are far more effective at ice removal at very low temperatures, from a safety point of view, is fantastic. The only problem is that from a concrete technology point of view, is a nightmare. And so we are causing all sorts of distress with the oxychloride reaction. Oxychloride doesn't form with sodium chloride. It does form far more rapidly with calcium and even more rapidly with the mag chloride systems. So changing our salts has suddenly made this a newfangled problem. I also suspect that there is an issue. There was a period of time when the stability of the air void system during handling was not quite as good as it used to be. Long, long ago, when Vinsol materials were the only air entraining agents, they were very stable. It was difficult to beat the good air void system out of the concrete. There was a time when we were flipping to alternative chemistry products. The stability was not quite there. So with a bit of vibration, you could actually implode or combine or beat out the smaller air bubbles. And so more than once, we would see cores where the entrained air was very, very low, despite field records telling us that at the point of delivery, the air was more than satisfactory. And so all we could impute out of that was that air was being lost. I think it's less of a problem nowadays. The admixture industry has heard this and have been addressing it. And the testing we've run recently has indicated that the modern products that we're getting today are a lot better than they were 10 years ago. I hope none of them come to shoot me. The other one, system chemistry. As fly ash changes, as cement changes, it's a fairly delicate chemical system. And again, as we modify our mixtures, this can be playing into why this is a modern problem. And finally, a lack of inspection. I have to tell a war story with this one. The photograph is here to remind me to do this. I was on a site. It was a 5 to 10-year-old pavement, and it looked really, really bad. The city engineer was biting my head off, promising never to build with concrete again because he was getting a severe de-icing salt or joint deterioration problem. After he had had his say and driven off angrily, a consulting engineer who was part of the group came up to me and took me down the road and pointed to this joint. And other than the farm growing in it, it's actually a beautiful joint. And his point is that the older pavement that was under distress, there had been no supervision. There had been no monitoring of the air void system, of the water cement ratio, of the supplementary cementing material dosage. We did not know what went into that pavement. The specs were all there, but there was no one verifying that it was compliant with the spec. After this consultant was engaged by the city to be an inspector, he was proud of the fact that he was a real pain. He bullied the contractors, he bullied the concrete suppliers, and insisted that they complied with the spec. And since then, the pavements have been performing perfectly satisfactorily. So again, this became a clue that, you know, oftentimes when we're playing with concrete mixtures, it's very easy to get them in trouble. And when we're in trouble, it's not a slope, a slide down. We fall off a cliff, and we go from being beautiful to really ugly, really, really quickly. The other part, I would encourage agencies, particularly local agencies, be aware of what's in your salt. Whenever I stand up and do this talk, I'll ask them, you know, what salt do you use? And many of them say the same as the DOT, and most state DOTs do not allow anything but sodium chloride. Then I start to quiz them about the products that they're buying. Oh yeah, we do buy that. Oh yeah, we do get that stuff. And the problem is that many of these products, I went into my local hardware store, found the first bag of salt that was near the front door, turned it over. Now it had a magic name of, it was a wonderful pixie dust that was promising to protect my plants, keep my driveway clean, and keep me safe, which is great until you read, not recommended for concrete less than 3 years old, not for cracked concrete. Intriguingly, it's not for precast concrete. I don't understand that one, because precast should be better quality than any field-placed concrete. But you start to realize, oh wait, this product is primarily magnesium chloride. And that's exactly the compound that is causing the problem. So again, my message to agencies is be aware of what you're buying, and make sure that you're aware of it all the way down the food chain. I've had it more than once. I speak to the chief maintenance engineer. Nope, we don't buy anything but sodium chloride. So then I go and speak to the foreman at the de-icing plant, and he says, nope, nothing but sodium chloride. Then you go and talk to the truck driver, and he says, yeah, right. There's all sorts of interesting stuff in the back of my truck. So again, what's in your salt is a fairly significant part of our process. Why does it happen in some joints and not others? I think part of it is batch variability, particularly in hand-placed concrete, because we all know the first thing that happens when a ready-mix truck arrives on a construction site, the foreman, without even looking up, says, add 10 gallons. And you immediately change your water-cement ratio. It may have been delivered at a 0.42. It's now at a 0.45. And that is enough of a cliff edge to take us over the edge. I've got more than one core set taken from good and bad places where the water-cement ratio is 4.2 in the good, 4.5 in the bad. Drainage, and I'll talk about drainage in a couple of slides' time. Soil treatment. I often see more distress in intersections than I do in the middle of a city block. Why? Because in the intersection, it's getting treated twice by the north-south treatment and the east-west treatment. And in fact, rumor has it is that the drivers will often open up the taps a little bit at the intersections. Why? Because of safety. Crashes happen at the intersections. We've got to get the ice out of those intersections faster. And so they get higher salt dosages. So, variability in our construction practices as our treatment practices can cause the variability that we're seeing between adjacent sections. So how do we prevent this thing? How do we summarize all of this rambling that I've been doing for the last 40 minutes? The weakest link is your weakest link. Look at the photograph of the fence. This was $1 billion fence around a university campus. And you can see that it's been carefully locked and secured with a twig. Fat lot of good it's doing. Okay, maybe it'll keep the animals out, but anybody who's driving that road on the outside of the property can get in. So security has been compromised. So we have to work hard at preventing saturation, making sure our drainage details right. we have to work hard at getting low permeability concrete, which means the right amount of the right supplementary cementing materials with a low water cement ratio and a good air void system. We have to make sure that all of these belts and braces are in place every time. The photograph on the left, I believe Minnesota started to play with this idea of a geotextile underneath the joints to help drain any water that gets through the joint out of the system and daylight it and get it away. And so we prevent that distress in the curve that we've seen in so many of the photographs so far. The other part to think about is, where did the water come from? This photograph was taken in a parking lot with a very large snow pile. I was standing on the snow pile, and you could see it was spring, it was starting to melt, and the melt was going into the joints. We were still going through a few freeze-thaw cycles. So this joint, the longitudinal joint, dry, far less distress. This joint, wet, and there you can see the trouble happening up and down here. Right? Where does the water come from? Are we making sure that we get it out of the system? Where can it go? If it gets through a joint and into a clay layer, it doesn't help us. In fact, I've got photographs taken out of parking lots where the water table is above the top surface of the concrete. The signs of the water traveling up through the joints and flowing away down the surface. Those pavements are in trouble. What about what's in the joints? So I think I got some other photographs to illustrate these. Where can the water go? We actually have a little toy that can measure the permeability of the base underneath the concrete when we pull a core. And this was one of the examples where we had fairly significant joint deterioration. We measured the permeability of the base material. It was very low. The water was not getting away. So water that, if your black seal fails, water gets past it and it can't go anywhere, you're doomed. The other part of it is, if you have edge drains or drainage systems, if they're full of plants, growth, algae, animal droppings, nests, it looks like a beehive in this photograph, of course, it's not going to drain. And so the system's going to get wet. We're going to go through the freeze-thaw or distress. All right. The third one, what about inside the joints? Well, you've seen this photograph before. If the water can't get away, it's trapped inside this kerf. This is where the issue is going to be. And so one of our recommendations is, forget about the backer rod, fill the whole thing up with sealant. It's not so much sealant as filler. And these photographs fairly clearly indicate where you have a large space for water to collect and do its trouble, we have quite a lot of trouble. On the other hand, where it's been filled, there's less water available. And so the rate of distress is significantly lower. This is a policy that Iowa DOT has adopted. They're not putting backer rods in, they're just filling the whole thing up, and seem to be reasonably happy with it so far. Photograph taken from some cores that Maria Maston from Minnesota DOT, she pulled, I can't remember, it was 160 odd cores from around the state to look at, does the low water cement ratio system pay off? And one of the things that came out as a clue as they were looking at all of these cores is that where there's been significant cracking and expansion and the seal has failed, there is trouble. Where the seal has stayed intact, the concrete's in good shape. So again, supporting this idea, if you're going to have a seal, make sure you maintain it. It's all very well to put a seal down at the beginning of construction, but in 5 to 10 years' time, you likely have to go back and repair it. If you don't, you may be then starting down this route of trouble. So how do we monitor this thing? This photograph hasn't very clear. This is a photograph that shows a little bit of shadowing in 2010 on a street in downtown Ames. We pulled a core from this. The concrete looked fine. We thought, okay, it's not so bad. We ignored it. I went out this morning to the same piece of roadway. It may not be the same joint, but it's certainly the same section. And you can see that in 10 years, it has reamed its way out. So shadowing is a first early indicator. We think that the cause of the shadowing is very early, subtle microcracking that holds water. It shows up more after a rain event because the water is trapped in those microcracks. But eventually it does start to show this sort of distress. All right. You also see spalling. You've seen the photo on the right before. I've already talked about how it steps its way up. What's intriguing is that if you break off one of these little pieces, it's solid, it's sound. So the crack is jumping and then progressing upwards. It seems to be only to the depth of the saw cut. So again, spalling is a fairly loud clue. The other clue may be faulting. And this is from an example where the engineer first knew he had a problem when he sent a team out to go and replace the mastic in his joints. So they pulled up the backer rod and started pouring mastic into the hole, and they used up their full day's supply in the first couple of joints. So then they went back out and pulled this core out and realized that even though it looked fine at the surface, there was all sorts of trouble below. And they'd actually lost all of their aggregate interlock because they lost all of their concrete. And so it explained the faulting they were seeing, and was, again, a result of freeze-thaw oxychloride formation below the backer rod. We can try and monitor it with devices like the mirror, FWD, and GPR. The mirror we can use to tell whether or not the crack is joint out. And Kyle Hook works for Minnesota DOT. He may have a better answer than me. I know he was looking at it at one stage. Whether or not you could tell whether or not it's just cracked or whether there is actually deterioration in the void, even though the surface looks fine. I'd be intrigued to learn more about whether or not it can do that for us. But there are tools out there, particularly with the FWD, to help us understand load transfer, maybe a fairly effective way. Otherwise, just watch it. You're going to see it in, in the form of shadowing and spalling. All right, I have got 10, 15 minutes left. And let's talk about, okay, so you've got a problem. What are we going to do about it? One of the quick and dirty solutions is to apply a penetrating sealant. There are a lot of different products out there. At this stage, I'm not sure that I know which ones work and which ones don't. John Kevin, we're working with John Kevin out of University of Missouri, Kansas City, to develop a protocol to be able to assess the different range of products. There's all sorts of chemistries, different modes of action, and we're halfway through that research project right at the moment. So give us another year, and we'll be able to give you some guidance on how to evaluate whether or not a given product is working. Most of them are pretty cheap, and so I don't have too much heartburn saying, yeah, go ahead and spray a product on. It'll buy you some time. How much? I'm not sure, but we've done a few field trials. We, in Iowa, several cities cooperated with us. We've sprayed these products on several different sections. Haven't been back to look at them for a couple of years and need to. Certainly a couple of them did buy us at least a couple of years. And that's always a good thing. At least gives you an opportunity to start saving up for other more significant repair approaches. The other thought may be to put a sealant in very early on, just to provide, again, more belts and braces to protect the inside the curve. If you're going to put a sealant in, you're going to have to pull the old mastic and backer rod out and then replace it. Just spraying around those, I'm not convinced is particularly helpful. We've done it in one demonstration project. We haven't got any data back yet on it as to whether or not it made a difference. But yeah, sealants are one thing to think about. The next step is to consider partial depth repairs. And again, Minnesota lead the way in expertise. The guidance documents that we have produced were based on stuff that we learned from Minnesota. So you guys know what you're doing. I don't need to talk about it a whole hell of a lot. But again, partial depths only work if you can stay above the steel. The moment the damage goes through the full depth of the distress, partials are not going to be particularly effective. The other trick with partials is choose your repair patch mixture carefully, because it's all very well to have a wonderful patch, but it only lasts 2 years. The traveling public tends to get pretty grumpy pretty quickly. And once again, I think the Minnesota DOT has a system that they like and seems to be working for them. And I'd refer you to the DOT for guidance on what their tried and true mixture is. The other one is, again, if you try and do a partial depth on a system that's faulted and moving pretty badly, it's just going to fail. The crack is going to go through the partial depth unless you put a debonding layer moving. Make sure that it can move with the way that the slabs are moving later on. Otherwise, you're just re-inviting issues. So attention to detail, think like engineers, be aware of all that's going on inside your pavement. Band-aids don't help an awful lot on a system that's moving. All right, if the depth of damage is all the way through or at least past the steel, or you have a loss of load transfer, then we have to think about full depth repairs. And again, Minnesota is well versed. I think I took this photo in Minnesota, or one very much like it. And again, there is a lot of guidance and documentation out there on how to do this effectively, but the basic idea is rip out the whole panel, cut it off, drill in and replace dowels to provide load transfer, make sure that your base layer is at least smooth, and put in a new surface. The one art with this is choosing when do you give up on patching and when you go to a complete replacement, because if you're patching every joint down a 1 mile section, the economics may not play out. So again, look at that one pretty carefully. If it's just a few joints, this is a very effective way of getting your ride quality back. But if every joint is shot, you may want to look at it a little carefully. Is that if you're replacing 80% of the system, the economics probably won't work. The other approach is to look at overlays, particularly with unbonded overlays, is that, again, you can separate the new layer from the old layer. So again, if it's moving, if there's quite a lot of distress, you can just fill the holes, put a separation layer in the form of geotextile or asphalt over it, and put a new layer of concrete over the top. This works really well if you don't have any elevation issues. But if you're in a downtown situation where you have a lot of driveways, manholes, drainage systems, overhead structures, you have to pay quite a lot of attention to what are you doing to your elevations. So detail can be challenging. It can be done. There are examples all over the Midwest where this has been achieved. I think this photograph was in Detroit. And that system has been in place for more than 10 years and is doing very nicely. But again, attention to detail is huge. And again, the other thing I would emphasize is that if you're putting in an overlay, make sure it's draining. I've seen mill and fill exercises fail because water gets past the joints into the debonding layer, whether it's asphalt or geotextile, and particularly with asphalt. If you have an asphalt debonding layer, water gets in there, it strips out, then you haven't got any support left, and then the whole thing fails. Alternatively, if you put in a geotextile and don't get it into an edge drain that is open, or daylight it, once again, water trapped in that geotextile will start to eat away your concrete from below with freeze-thaw and oxychloride reactions. So again, drainage, drainage, drainage. It's a bit like the 3 rules of buying property. It's not location, it's drainage. For guidance on overlays in this application, there is a document available from the center, and I believe Lauren's going to be emailing out a link to this document after the session is over. The alternative is, if it's bad enough and deep enough and extensive enough, you have to rip the whole thing out and start all over again. But hopefully we can get to it before it gets that bad with partials and full depths, or at worst, an overlay, and keep some value in the investment, the infrastructure that we already have in place. And that is about it. So the questions we want to ask you: how does your agency monitor the condition of your joints? Are you doing anything other than watching for shadowing, keeping an eye on spalling, waiting for the mayor's wife to phone you and complain that she broke a heel? That sounds facetious, but I've actually heard it happen. There was distress happening in a city hall parking lot, and the mayor's wife broke a heel, and within 2 hours, we had been called out to go and have a look at it. So, yeah. Right. How does your agency investigate deteriorated joints? Once you started to see the distress, how do you know that it's, while the surface is looking good, there's nothing happening underneath? Are you using tools other than the approaches that we've talked about? Do you have a standard set of rehabilitation approaches, strategies? Again, if you're doing anything differently from what we described, we'd love to know about it, because any guidance that we can provide to your friends and neighbors would be fantastic. What process do you use to choose between repair strategies? Do you have any case studies? Do we miss anything? We're desperate to learn from you, and we sure appreciate you responding to the survey that Lauren will be sending out. Again, there is some guidance. We published a document in 2016. It was written by Jason Weiss, so it's full of real great expertise, and it's a free download from our website. The link to that will also be provided. If anybody wants a copy of the slide set, feel free to contact me, and I'll be happy to send you a PDF with it. I'm also looking at seeing whether or not I can post the slide set on our website somewhere. Haven't done that yet, but I'm quite happy to share the information with you if you want it. And with that, I am done. I'm happy to hand it back over to Joe. I don't know if anybody has any questions. Probably, as I said, the easiest way maybe to throw things in the chat box and we can try and address them.
All right, thank you, Peter. Does anybody have any questions for Peter while he's still in the line here about his presentation? It's very good.
We do have a question in the Q&A section.
Oh, I don't know where to find that on my.
Can you read it out, Lauren?
Yeah, I'm not able to see that.
Sure, you might have to click the little down button or the side button arrow to see the drop down the Q&A box. Should be on the right-hand side, but I can read it for you. Based on slide 13, with the apparent fly ash shortage, will we be building pavements to fail if there is no fly ash in the mix?
I was hoping no one would ask that question. Fly ash helps. I think we can develop other strategies to at least protect ourselves to some degree. Slag is wonderful. Metakaolin is a wonderful product if you can get it. Otherwise, pay attention to water cement ratio and the air void system to provide some protection. But yeah, as I said, I'm hoping to do a webinar in about a month hosted by ARM, and we'll be trying to speak to that topic. So watch this space is all I can say for now. Okay, I think I can see the questions. The next one, vibrators turned up too high can cause low air. Absolutely. We have a wonderful example here in Des Moines where the mixture was very harsh. It was chewy and lumpy. And the contractor's solution to this very dry mix was to run his vibrators at about 13,000 VPM. And now when you drive on that road, you can see where each vibrator ran, 18 inches apart for the length of the highway. The air has been beaten out, and there is stripes of concrete that is going through freeze-thaw distress. In between the vibrators, the concrete is fine, but above the vibrators, it's in a fair amount of trouble. We're actually working with vibrator manufacturers right at the moment to see if we can raise some funding to get a fundamental understanding of this topic. I think it's one we do have to pay attention to. So if anybody has a checkbook, wants to give me a shout, we've got the research program already set out. But and we've done some preliminary work, which is very clearly showing that the higher the frequency, you move the air vertically and you move the water horizontally, and both are bad. And so low vibration frequency is definitely to be recommended. All right, the next question. How do you quantify incompressible materials in a joint? I have no idea. Joe, if you want to speak to that one, other than to say, don't.
Yeah, I don't have a good answer for quantifying. Is it by volume or I'm not sure.
Yeah.
I think the wider your joints, obviously, the more opportunity, and if they're unsealed as well.
Right. I guess where I have seen it is that if you get a little pebble in, I've often seen spalling with a pebble left over. You know, and this comes back to the question, do you seal or not seal a joint? And I really don't want to get into that debate, but if you have a wide joint, sealing is necessary. If you have a relatively narrow joint, 1/16 of an inch, 1/8 of an inch, you may get away with not sealing it, particularly in high-speed applications. But then you still risk the joint filling up, not so much with pebbles, but with crud. And that worries me, not so much with joint deterioration, but blow-ups. That's a whole nother topic. That's another webinar right there. So we'll come back to that one later. Okay, what's my opinion on sealed or unsealed? Again, if it's a wide open joint, if you've sawn it to 1/4 inch, you got to seal it and fill it and keep it sealed. And what I would do is default to ACPA has published a good document with current thinking on the seal, no seal issue. And I'd recommend that you access that. If you need a link to it, get in touch with me and I'll send you a link. All right, Larry Sutter has an interesting presentation on the future of fly ash and the abundance of reclaimable fly ash. Yes, he does. And in fact, I think he spoke at an NRA and certainly at a Minnesota Concrete Council session recently. And this is probably the best hope for us in the future with fly ash, is that as we begin to build up the ability to reclaim fly ash from landfill, it can start to substitute for collecting fly ash as it's produced. And Larry has written a very good tech brief for us. We are going to be publishing that under an FHWA logo as soon as we can get it past the Fed legal system. So yeah, that information is in hand and will be published as soon as we can get permission to do so. All right. Those are all the questions I'm seeing.
Anybody else have anything quickly? Okay, then. Really want to say thank you, Peter, for the time. And please, everybody on this webinar will get a link, receive a link sent to them for the survey that was assembled for Peter's project here. And so if you could respond to that, that would be extremely helpful. Is there anything else you want to finish up, Peter, on the either on the survey or anything to follow from that? Okay, then I think with that, I think we're finished. So thanks everybody for joining us.